Now I'm delighted to introduce to you all Jonathan Armstrong, a machine learning KTP at Cirdan. He's going to talk to you today about how to get started with AI and ML.
Thank you very much, everybody, for coming. And I appreciate to the organizers the opportunity to share a little bit of my story in AI and let's say a few suggestions I would have around anybody on the call here getting started, as well as some of the interesting projects I've had the opportunity to be working on or have worked on in the past. My name is Jonathan Armstrong. I'm a machine learning engineer at Cirdan. They're a medical imaging and data analytics pathology company in Lisbon. I'm currently doing a computer science PhD with Queen's University Belfast on deep learning for digital pathology. And I have a mechanical engineering degree from Federal University in South Brazil. So that last comment might have given you a small hint, but I just wanted to ask the question, or wondered if anybody could tell me the link between these two images. So this is a coal-fired power plant in the north of Brazil, and also a picture of a breast mammogram. And really, the very interesting link between that is artificial intelligence and then also me. So I started out my journey really, my parents are missionaries in Brazil, and I started out and I did mechanical engineering, a degree in mechanical engineering, and it really stemmed from a conversation I had with a friend of the family's who's a surgeon in England, really because I was very interested in getting into biomedical engineering, but I didn't have that exact course to do. And he said, well, do mechanical engineering because you'll get a lot of experience and a broad spectrum of study, and then you can decide where you're going later. So it's very interesting to now have come full circle and now not actually be in the mechanical side of biomedical engineering, but really the software side and the analytics and AI side of biomedical engineering. So by the end of my dissertation, I ended up joining, or by the end of my degree, I ended up joining a lab, a thermal lab in the university, and they were working on a 2-year project around a coal-fired power plant. And our goal was to model that power plant in various different ways, maybe looking at the thermal analysis, the flow analysis of it, but then also AI was one of the ways we were going to look at it. And so we applied AI to look at the input of coal, the humidity, the dampness of the coal, the amount of ash, strange things, but then looking at the output of electricity at the other end. And so that experience in AI with the data and with the results then meant I was able to apply for a job that appeared in the KTP program with Queen's in AI and medical imaging at Cirdan. So the KTP stands for Knowledge Transfer Partnership. That is transferring knowledge from a university into a private company that is key to the company's development. And then also, along with Cirdan, I started a PhD in deep learning for digital pathology. So you might be maybe sitting on this call, and I saw an interesting poll there. Quite a few of you are just interested in knowing where to start really with AI. I know some people will already, this is old hat, but where to start? Well, a lot of times you could maybe just do like I did, look at it for your dissertation. I did a degree in mechanical engineering. So, you know, if you're working with audio, you're working with medical side of things, computer science, engineering, anything that is very much data driven can be analyzed with AI. And as long as you know how to apply the tools right and do some research into that, that could be a very interesting way of starting. There's also the KTP project. There's an awful lot of, I think Queen's has around 50 KTP projects ongoing at the minute. And speaking to one of my advisors recently, he said that around 60% of the KTP projects already involve AI somewhat in those projects. PhD or further studies are another interesting way of getting into this area. But the reality is everybody can start at home. You can start where you are by just looking at some helpful resources. And that's where I got an awful lot of my initial learning in machine learning and AI. And I just wanted to list a few helpful resources that I find. For example, Microsoft AI School. They have a lot of very interesting, good, free courses anybody can do. If you want a certificate, you can pay for it, but the course in itself is free. Kaggle, for example. Kaggle is a site that they offer an awful lot of open data sets and challenges that people can then use this data to apply their AI skills, follow what somebody else has done, and learn that way. There's some very good YouTube tutorials that I found as well, or you could do Udemy courses, find some paid courses. But I have here just a list of courses and things that really helped me to get started, and I'm very happy to share this by email with the organizers later, that they can share to the rest of you then if there's any interest. But feel free to reach out to me on that as well. And the reality is, what I say to you is, don't be afraid to get involved, but just be aware that machine learning is a tool. And in order to use a tool, you need to know intrinsically how the tool works. And it's knowledge of how the tool works and knowledge of the data that you're applying that tool to that is crucial for you to get a good project. And so just a little word of caution, and I think this is exemplified by the Gartner Hype Curve. I'm not sure if anybody's familiar with that, but it's a curve that looks at emerging technologies. It looks at them along the bottom axis really looks at sort of the human feeling on it. And your danger is when you're in this area here, that people have inflated expectations, because that's where everybody thinks that this is the bee's knees. It's going to do everything. It's going to solve all our problems. And in 2018, deep learning and neural networks was right at the very top of that. Now, it's more interesting to look at the 2020 Gartner Hype Curve. It sort of expanded a bit. There's now 6 AI machine learning related subjects. People have seemed to get a better grasp of what's really happening, but also, explainable AI, being able to understand what the black box is saying. That's still something that's very much at the peak of inflated expectations. And to me, it's important to stay grounded in your data, grounded in your knowledge of how you're applying that, so that when you come to the trough of disillusionment, when you come to that point where people are saying, well, it's maybe not all it's meant to be, that you've already passed that peak of inflated expectations and know how to apply this tool really well. So I thought it would be interesting as well to just cover a wee bit for people who maybe aren't familiar with AI really at all. How does it actually work? What's happening on a very basic level with a basic example? How do the machines learn? And that's why I don't like calling it artificial intelligence. It sounds like something scary and sci-fi. The reality is it's machine learning. It's a statistical model of a certain amount of information. That's the way it works. But let's take an example. For example, your times tables. You started out with a problem, 5 times 5, and a result, 25. And you move down, and it's through repetition that you actually started to learn your times tables. You tested your knowledge by maybe a parent or a teacher asking you the times tables. And then with the principles you'd learned from your times tables, you could go out and say, well, I hadn't learned up to 5 times 11, but it's 55. That's really the way it works with an algorithm. You need data, you need a problem and a result. Whether that's an image, a little image, and it says cancer, not cancer, whether that is input data and an output of electricity like the power plant, but through repetition, the algorithms will learn and they'll check against themselves with testing their knowledge. It's called validation. So you've got your training, it learns, your validation, it's testing, and then finally, things it hasn't seen before is your final testing to make sure you've got a really robust algorithm. So normally you start out with your data. In any algorithm, you'll start out with data. The common thing to do is divide it into 2 or 3 parts, normally training and validation, and maybe an extra 10% for that testing I mentioned. But based on your training, you train your algorithm, you check it against the validation, and then it's upon the comparison of these validation accuracy and your algorithm accuracy. If they're both close together, it means that your algorithm is, yes, learning with the data it's been given, learning with the things it hasn't actually seen that much yet, and it means you've got a good, robust algorithm. If that's not the case, if you've got a high accuracy but a low validation accuracy, it means it's really just learnt the images off. It knows the thing off by heart, but it hasn't really understood the underlying information in that. So in other words, it's just learnt the timetable off by heart, but it hasn't really understood them. And now the times table is a bit of a funny example because obviously AI isn't to be used for times tables. That goes back to my previous comment that you need to know your data and the tool and how to apply it. You need to be aware that sometimes there's a far simpler way of getting sound information out of the data, not just through AI. And it all boils down to the simple comment, and to quote, Bill Clinton, to paraphrase Bill Clinton, it's all in the data, stupid. Everything is data dependent. The problem is always in the data. Well, virtually always. The odd time you've a bug in your code or an error in the Python environment, that's beside the point. It's through your data and understanding your data. And if you've got biased data to, for example, years ago, Amazon used it to decide the initial decision on the CVs that they were for new applicants. But they had a really bad algorithm that only suggested male CVs, only employed men, because they had trained it on historic data. Historically, they had employed more men than women, so the algorithm just made that decision for them. And that's where you need to be aware of your data to then apply this tool. So I thought it'd be interesting just then to cover a few of the current projects that I'm working on in Cirdan. And they really all center around a very specific area, which is the screening programs that are ongoing in the UK, which are medical programs that are to catch the early forms of cancer. There's a bowel cancer screening program, which involves a colonoscopy and whole slide images from digital pathology. Or there's the breast cancer screening program, which involves mammographies or mammograms. So those are more X-ray style of images. So I've been working on 3 different projects, really, mainly starting out with the mammograms, starting to be able to identify anomalies, using AI, identifying anomalies in mammograms, then really focusing, applying that learning to Cirdan's own problem. We have a little X-ray cabinet where we look at biopsies that come out of these mammogram tests, and we look at them in an X-ray form, and I'll show you a few images, explain it a bit better later. And then finally looking at the outcome of the bowel cancer screening program, these colon polyps. So those are the 3 areas. They're all image driven, but we plan to focus more on data analytics as well in the future. And the main motivation behind this is that in spite of all of these screening programs, they're excellent, but the difficulty is that they put a massive additional pressure on clinicians. And so only 1 in 5 UK trusts in radiology have enough radiologists to run a safe 24/7 service. And that costs the NHS, a couple of years ago actually now, it cost them 165 million in outsourcing to places even like Australia, sending those images, those mammograms, those X-rays to Australia to get them diagnosed overnight to come back to you here. Pathology, same story, only even less. There's only 3% of UK pathology labs have enough staff to meet the clinical demand. And that costs around 27 million a year across the UK. So that gives you an idea of the need. And it's not even as if that need can be supplied really quickly, because it takes you maybe 10 years, 15 years to train up a pathologist or a radiologist. So some drastic change needs to happen in the meantime. And that's where I've really appreciated being part of Cirdan, starting to look into those different areas, to those clinical pathways, to those workflows, to try and really make a difference. And our goal is to improve well-being through innovation. Cirdan works in various different areas. One is LIMS, not human limbs, but laboratory information management systems. So the software that controls labs. Also in medical imaging then, in X-rays and digital pathology slides. And so we're focusing on pathology analytics, and that's been really the main driver behind any projects I've done so far. And the initial start then has been around these mammograms. And I just wanted to sort of show you, exemplify a little bit of how what a project sort of looks like. Once you have your data, you have your results. These mammograms here's a few pictures of the mammograms from an open data set. These mammograms all came with a certain amount of background information. So what clinicians had identified as an anomalous region, a cancerous area. Those images then, as you see here on the right, and I've just put a little red circle to exemplify that is an anomalous, a cancerous region. Then they're transformed into a more algorithm readable way. So those are small patches, and we divide them into small patches. And so basically any patch that isn't within this red circle is defined as a negative patch, has no cancer. Any patch that was in the red circle is a positive patch. And so you're now back to where we discussed at the start. You've got your data and you've got your result. You've got your problem, cancer, not cancer, and the result. This is a cancerous patch. This isn't a cancerous patch. And so training the algorithm on that, then was able to develop an algorithm that identified going through a mammogram, was able to by itself in 15 seconds start putting on these outputs, as you can see here. And this it correctly diagnosed an anomalous patch. And so from an open data set, you can start to extract really interesting information and then apply this finally to the needle biopsy images from our own private data set. And this algorithm here was trained to identify little precursor signs of cancer, which are little calcifications. You can see these little black dots. And so you can very well add information into the clinical pathway, add information onto what the clinician is seeing to help them make a more informed decision. And it's really the same then going into the colon polyps. Colon polyps are skin tags that develop. The earlier you catch them, the better. Based on what the skin tags look like, let's say, then you decide the person's further treatment. And here's like just a little progression of how the colon polyps progress. It's a little skin tag that then can become cancerous and dangerous. But what does the clinician look at? Well, they do a colonoscopy. They extract those little patches, those little, polyps. Those polyps are then turned into whole slide images. So as you can see here, here's basically a cross section of one of these little polyps. And you can see you can see this darker region here with a sort of funnily, more mottly growth. Those are anomalous regions. Those are cancerous regions. And based on the diagnosis of those regions is what you decide the person's clinical pathway, whether they come back every year for a checkup or every 5 years for a checkup, or they don't need another checkup. And so the clinician really in this case, they want to identify what the polyp is, give it a classification, how serious it is, maybe look at the area, but output that to a report. And so it's crucial to speak to the clinicians or the people who know the data and see what they want out of the data, what their pathway is, so they get the images and turn it into what? A report. And so based on that, then we have collected with the Royal Victoria Hospital 500 fully annotated slides, working with Dr. Maurice Lochry in the Royal as part of a project to get these slides annotated to then create this boundary, as you can see here. And based on this boundary, then you start to train your algorithm. But no longer are you using positive and negative patches like I showed before, but now with this mask here, you can start training the algorithm on an input image and an output image. And so at the end of this, with lots of training, you could start to get the algorithm to output basically this exact picture here based on a normal slide image. So really the key takeaways I would like to just share with the folks here today is there's nothing really to stop you starting now in AI. There's an awful lot of open data sets, an awful lot of open opportunities all around. With a bit of experience, you'll be able to use or apply for jobs or use it for other things. The key in all of it is the data. You need to know where your data is coming from and know your data intrinsically to then be able to apply the tool. You need to also listen to the people from whom you got the data or study the data and understand what they actually want, what decisions they want to make coming from that data. And the goal, the overarching goal in my projects and for Cirdan is to maximize the use of clinical time so that they don't need to see all of those normal bits of information. So they don't need to have their work lists packed up with too much information. They can mainly use their time on things that matter, and you enrich the whole decision-making process and even may make different studies and analysis that people haven't actually seen before. So thank you very much, everybody. I hope that wasn't too fast, but I hope that gave you a bit of an insight to how AI is being applied in the medical sphere, at least, and a wee bit of my pathway in it.
Thanks very much, Jonathan. That talk was very insightful and interesting. Enough to open the floor to the attendees. If you want to ask any questions, you can pop them in the chat, or alternatively, you can unmute your mic.
Jonathan, it's Philip Patterson here. Was it very interesting what you're doing, and it's very insightful to what you're going through and very important. The training part of it, how do you go about that? Is that built in inside the tool around the training, or which way does that work?
The training part is normally I use a language called TensorFlow. So it's a way it builds out a network. So you define your shape of the network. Normally you use networks that have already been used in the past, that sort of thing, that have an awful lot of research behind them. And those networks, really, their sole goal is to look at an image or look at data and compress that down and nearly linearize it into decisions. And it'll apply little filters right across, for example, an image, and start picking out features, let's say, that make that decision process. But you run through hundreds of thousands of images each time and do maybe 100 iterations over your model until you get a good high enough accuracy. And that's really where your training comes from. Okay. And really, I don't know if that answers your question.
The images that you're putting in, do you know the outputs of the?
Yes.
They are. So then your training is then you're validating against the images that you put through. Is that the way you would do it?
Well, normally you keep those images separate that you're validating against, but yes, you.
Okay.
But what I've been doing is supervised learning, which means you need to know the input and the output. So you show it an input and an output, iterate over that, and then it's be able to make decisions on images it hasn't really seen yet.
Okay, great, good, thank you.
Thank you.
Jonathan, quick one for me. You went from mechanical engineering to what is now really AI engineering. How on earth did you make that jump?
Well, I've always been fascinated by AI, always sounded interesting. And I was doing my dissertation just at the very peak of that hype curve that I showed at the start. So it was very interesting, and to be able to apply that to model a power plant was a very interesting option. And to then find a job in that sphere really was just the next goal. Or I'd been thinking of either a job or then doing maybe a master in data analytics and machine learning, that sort of thing. It was more that jump of using it as a tool, being a specialist somewhat in an area, using it as an additional tool, and then really fell in love with the tool and moved on from there.
Fair play, congrats.
Thank you. Thanks for your question.
I have a wee question for you, Jonathan.
Absolutely.
I was wondering, with your collaboration with the local hospital here, do the patients volunteer their data, or what sort of way does that work?
So that's something that we have to be very careful with. We needed to get full ethical approval from the Northern Ireland Biobank to be able to then use these images and scan them. Granted, in the screening program, in the bowel cancer screening program, part of the what patient signs up to be part of the bowel cancer screening program to get this screening is that their data or their images might be used for clinical research in the future. It's totally anonymized. We haven't a clue of that, what's happened in behind those images, but we do have that diagnosis from a specialist for each one of those images.
I was wondering how the ethics of that would work. That's really interesting. I have one more question, just with your personal experience in your daily job. What sort of technologies and languages would you use specifically to analyze these images?
Really Python. And so I ended up learning Python for AI machine learning and progressing into some of the main deep learning machine learning libraries. So that's a TensorFlow, Keras, PyTorch. Those are the main libraries around deep learning. And you know, they're very much geared to this exact problem, and everybody uses either TensorFlow or PyTorch. I'm in the PyTorch side, on the TensorFlow side, sorry, but they're both pretty similar, I believe.
Oh, that's brilliant. Even those keywords are worth sharing for people to look up. I haven't heard of PyTorch myself, so that's something
It's
to
another
learn about.
equivalent language, yes, to Keras, to TensorFlow, sorry. And Keras really is a more high level language, but then can have, you know, a Keras form of TensorFlow. So TensorFlow is your more granular way, and that's really why you end up doing research in it, is to sort of get those little small amounts, percentage improvements. Yes, you could apply an online tool, but the reality is, to really get a good understanding and a sound algorithm, you need to be applying it from start to finish and understand the process.
Thanks so much, Jonathan. That was really insightful
Okay.
and informative.
Thank you very much then.
Thank you.